All right. Good morning, everybody. Welcome to my live today. My name is Professor TK, the chemist, and today I am going to give you guys some information that you need to know based on colligative properties and the freezing point and boiling point of solutions. What I know is that for students who are learning this particular session, they may have problems with this if they don't know the proper steps they need to encounter or go through. So let's go ahead and get into why this is going to be a very important process for many of you all that are on this particular unit. One thing I need to kind of share with you is that as we go through these problems, what you will find on the board are some examples of um, of the formulas that we're going to use. And we talked about this previously. However, I do know, and I am very mindful of the fact that many of you all may not know what this all represents and what it means. So whenever you look at a problem, you may not be familiar with the steps and procedures that you would have to go through in order to understand how all of this works. So what I'm going to do right now is kind of walk you all through this whole process on colligative properties so that you all will understand what this all represents and what it means, okay? So let me go ahead and screen share a different screen so that you all can have some further clarity on this whole process of colligative properties. So let me go ahead and pull a couple of things up for you guys, all right? And of course, if you all have questions about anything that I am presenting within my video, make sure you guys reach out to me. Let me know, hey, Professor TK, can you go back over this problem? Can you give me a better idea of what I need to know for this problem, okay? Because I know a lot of times students do have trouble understanding this information, and you may not always get what you need right then and there, but there are points that you can actually go through to get further clarity. So what I wanted to show you, whenever you're talking about the freezing point depression, what you have to keep in mind is that there are certain key factors within the formula that you will have to know how to use, okay? If you know how to use them, that makes life a whole lot easier, okay? A whole lot easier. So let me go ahead and dial back a little bit and go through this one part of the worksheet that I think you guys would be very happy to know how to use it. All right. So whenever you talk about colligative properties and all of that good stuff, there are some key factors here that you all need to know. One thing is this formula that I presented to you all previously deals with the fact that delta T of F is equal to K of F times M, which is molality, times the Van 't Hoff factor. Now, if you don't know what each of those things mean, that's where the trouble will come into play. All right. So what I'm going to do. All right. Good morning, She Means Business. How are you doing today? So what I'm going to do is I am going to give you all the ideas that can help you understand this process. Now, when I presented this information yesterday, I realized that several students did not quite understand what we were discussing as it relates to these formulas. So let me go through them with you all again to kind of bring further clarity to what you have to know. So the Van Hoff constant, this little I here that's a part of the formula. This is one of the things that you must understand. How this works is the Van Hoff factor tells us how many pieces of substance breaks in two when it's mixed with water. Okay? It tells us how many pieces a substance breaks into when it's mixed with water. So let's say, for instance, that you have a cookie, right? And you dunk it in water. If the cookie doesn't break, then this little I will become one. But let's say that the cookie breaks into two particles or two pieces, then that little I becomes two. If the cookie breaks into three pieces, you got it, then the I will become three. So this is exactly how chemicals behave in water. Some stay whole like sugar because it's a non-electrolyte. Well, while others will actually break apart like salt because it is an electrolyte. So that brings me to the other point of reference that you guys need to know. In order to determine what the Van Hoff factor is, you have to know if the substance is either a non-electrolyte or an electrolyte. Once you know that, everything else will come to life. Okay. Now, I bring that up because when we go through some of these word problems, you're going to have to know that main part in order to establish clarity for what we're doing. Okay. Now, with the molality, we talked about this yesterday as well. For molality, the formula for molality is equal to the moles of the solute divided by the kilograms of the solvent. So, in other words, in order to use this formula, you would have to take whatever the solute is. If it's in grams, which more than likely it will be, you'll have to convert those grams to a mole by simply dividing by the molar mass, okay? So you would have to know the molar mass of whatever the solute is. And then your solvent is water, okay? And then you would have to know the kilograms of that. All right. So that's the other thing. So when you do problems like this, utilizing these three variables, you typically have additional steps unless they give you the molality, like point blank period. They give you the molality that you don't have to calculate, but it's already given to you in the problem. Then this would be a one-step process. Okay. And of course, your K of F, which is your freezing point depression constant, that's going to also be a number that you can look up in the back of your textbook, and or it'll be given within the problem itself. Now, why am I saying all of this? I'm saying all this because when we were looking at these problems yesterday, we have to understand that one, the I that's given the Van Hoff constant, you or factor, you have to know that particular part to get your answer right. So you have to know if you're dealing with non-electrolytes or electrolytes. Secondly, molality. Molality, okay, which is this formula right here. Molality has to also be calculated within your problem if it's not already provided, okay? So that's what made those problems from yesterday appear very long. So I'm going to give you all some examples today that's going to kind of express how all of this will work so that it's not going to be as difficult as it appeared to be on yesterday. Okay. So we're going to go through these examples here just to make sure you guys are good to go. So let me go ahead and share my screen on another example. Okay. So right here, you've got, even though it says rank the following solutions from the highest boiling point to the lowest boiling point, what I'm going to do for right now, we're just going to calculate the I. In order to determine the highest boiling point versus the lowest boiling point, you have to calculate the I, which is the Van Hoff factor. Okay. That's what you have to do for this particular process. So what we're going to do just to kind of get you started, let's take a look at this first example right here. You've got 0.50 molality of sodium chloride. Letter B is 0.25 molality of potassium sulfate and 0.75 molality of glucose. Now, let me go ahead and kind of set these subscripts in the proper way so that you guys don't get confused when you see these, okay? So here's the thing that you guys got to be mindful of. These subscripts, depending on what the substance is, will indicate whether or not you're going to include them in your Van Hoff factor, okay? So here's what I mean as an example. In letter A, it doesn't matter what the molality is. What we're going to do is look at how many pieces this particular solute will break apart into. So sodium chloride is an electrolyte, therefore it will break apart. So in this case right here, we have one sodium ion plus one chlorine ion. So the Van Hoff factor is 2. because 1 plus 1 is 2. Now, when we look at letter B, we have K2SO4. Again, this is an electrolyte. How do I know that? Well, because you have potassium, okay, which is a positive metal. And then the sulfate ion is a polyatomic ion, which is negatively charged. This tells me that this will be an electrolyte. Now, because I know that, and because you know that as well, the K has a subscript of 2, and then we treat the polyatomic ion as one unit. So that's why I'm going to put plus 1 right there. So 2 plus 1 gives us 3. Now, if we look at the next one, C6H12O6, in this particular case right here, this is glucose. This is a non-electrolyte particle. Because sugar is a non-electrolyte particle, our I is automatically equal to 1. Okay? You have those carbons, hydrogens, and oxygens in this particular formula that's going to make this become a non-electrolyte, which means the I is equal to 1. Now, having said that, if I were to ask you to rank these from the highest boiling point to the lowest boiling point, what you have to be aware of the fact is the higher the number, the higher the number, the higher the boiling point. So that means K2SO4 is first, followed by NaCl, and then glucose. Okay. So right here, these are your boiling points rankings. K2SO4 has a higher Van't Hoff factor than sodium chloride, followed by glucose. Excuse me. Okay, so in other words, this is exactly how chemicals behave in water. So some will stay whole, like sugar. That's why it's 1. Whereas some of these will break apart, like salt and potassium sulfate. Okay, so those are some examples that you guys should be aware of. Now, why does this matter? Well, the stronger the effect it has on things, like breaking apart, it tends to affect the boiling point, the freezing point, and the osmotic pressure. Okay, so it's like adding more to the process. You're adding more solutes to the process of your solution. Okay. Now, in terms of healthcare, hospitals use this concept to make IV fluids, that are safe for your body. So if the solution has too many pieces, like a high I, meaning the high Van't Hoff factor, it could actually hurt your cells. But on the flip side, if it has too few pieces, it won't work properly. So that's why this is important for this part of the discussion. Okay? That's why this is important for our discussion. Now, if you talk about CSI, for instance, forensic scientists can actually use this same information to determine how a poison or a drug breaks apart in the body. Okay, so if they know the Van't Hoff factor, they can predict how strong or fast the chemicals will affect someone. So this is why we kind of go through this whole process. Okay, this is why we go through this process. Now, there are some practice problems that I want to get us to do, all right? And let me also say this too. I am going to give you, okay, some examples of how to utilize this. I'm going to give you like a formula, okay? A formula that will help you remember the order that you would have to do this, okay? So that's what I'm going to do right now is give you the formula or some step-by-steps on how to use this, all right? So right here, it says, okay, this is the main formula right here. Delta T of F is equal to I, the Van Hoff factor, times K of F, times molality. Now, again, you've seen this before. Sometimes you'll have the formulas that'll look the same. It'll look like this. And then other times they may put the K of F first, the M, and then the I. But either way it goes, this is how you're able to determine that particular process, okay? So here's your step-by-step guide so that you will know how to use this for all of your practice problems, okay? You will know how to use this for all of your practice problems. So here is another example, or here's your step-by-step. First thing you want to do, you're going to be given this formula right here, okay? However, there are things that you'll need to know in order to apply it. Number one, you want to find the molar mass of the solute. And how do you find the molar mass? You just use your periodic table to calculate the molar mass of the compound. Okay? Step two, you want to convert grams of the solute to the moles. All right, by using the molar mass of the solute from step one. So if they give you the grams of the solute in your problem, you're going to divide that by the molar mass. So that's how step one and step two go together. Now, when we look at step three, you're going to then convert the grams of your solvent to kilograms. So remember how I said that the grams of your solvent are typically water. You know, your water is usually your solvent. In most of the problems that we encounter, your solvent is going to be water. So in this case, they're going to give it to you in grams. You've got to convert it to kilograms by dividing by 1,000 or moving your decimal 3 places to the left. Okay? So let me put this here, or move the decimal 3 places to the left. Okay? And then in step 4, what you're going to do, you're going to combine step 2 and step 3 right here to give you the molality of that answer. Okay? So again, you're going to, for step 4, to calculate the molality, you're going to combine step 2 with step 3. So step two's answer is on the very top. Step three's answer is on the very bottom. And that's how you calculate molality. So the unit for molality is moles per kilogram, or just simply that little funny shaped M. It's like a curly M, okay? Now, in step 5, you have to determine the Van't Hoff factor. And we did that a second ago. Remember, your non-electrolytes, the I is automatically equal to 1. However, with your ionic compounds, you're going to count the number of ions that it breaks apart into. Like again, in this example before with sodium and chlorine, you're going to say, all right, there's 1 sodium, 1 chlorine. So your I is equal to 2. All right. So you're going to count those up, and then that's how you determine what the I is going to be. If they don't give you the I, this is how you do it. And then finally, you're going to use this formula here, okay? And guess what? This formula here is similar to the formula for a boiling point. So this is the freezing point depression, but the other one that's just like this, you replace the F with the B for boiling point. Okay? Same thing, same thing. In the event that you have to find the temperature of the solution, then you would take the pure solvent's temperature minus your delta T of F, which we just calculated. For pure water, it's equal to 0. And so that's why we tend to stop at step 6, unless otherwise noted, okay? Unless otherwise noted. Now, what I want to do is give you all some examples of how to use this formula right here, okay? Because I know several students are going to have questions about how do I use this whole process? How do I solve these problems? So what we're going to do is move our screen over. We're going to actually get into these examples here. And again, for those of you all that are watching the replay, make sure that you reach out to me. If you have further questions and you need clarity on these problems, make sure you reach out to me. Put a comment in the comment space below, okay? If you need further clarity. All right. So let's go ahead and transfer this process to a practice problem. All right. So here's your example here. Here's your first example. Okay. And I am going to give you all this. Here's your formula that I have highlighted for you. Okay. So that you guys can actually see how simple this can be. All right. So in our first problem right here, there we go. This is the formula that we're going to use, okay? And this is your first problem. This is a CSI poison analysis. Guys, I love giving problems like this because students don't understand why they have to know this until you give them a real life example. So this is why I'm doing problems of this nature right here, okay? Just FYI, okay? So it says a lab tech finds a sample with a freezing point of negative 2.48 degrees Celsius. The solute is barium chloride, which dissociates into three ions. The solution used 1.00 kilograms of water and contained 0.050 moles of barium chloride. If K of F is equal to 1.86 degrees Celsius per molality, what is the expected freezing point? Solve for delta T of F and confirm final freezing point. All right. Now, in this problem right here, let's analyze what was given. They told you that your I was 3. And how do you know that? Well, here was your formula right here, barium, and then you have chlorine. So 1 plus 2 gives you 3. That's how you get those 3 ions. They also told you that you have in the solution 1.00 kilograms of water. And guess what? That is equal to your solvent right there. And they already put it in kilograms, so you don't have to worry about doing that. Okay. They've already converted it for you. And then they also told us the moles, 0.050 moles of barium chloride. So what you're going to do, okay, you're going to take these two numbers, and this is your solute. Remember, molality, this little funny shaped M, is equal to the moles per kilograms, okay? The moles of your solute divided by the kilograms of your solvent. So the moles here in this case was 0.050 moles, and we're going to divide that by, excuse me, 1.00 kilograms. Well, when we divide those two numbers, we get 0.050 and that little funny shaped M. Okay? Now the K of F, they gave you that as well, which was the 1.86 degrees Celsius molality. So we actually have all three of our numbers that we need to solve this problem. So let's go ahead and plug this into our format here, our formula, okay? So let me go ahead and write that in for you guys. Delta T of F is equal to the I times the K of F times molality. Okay, so what am I going to do is plug those numbers in. My I here was 3. My K of F was 1.86 degrees Celsius per molality times molality here, which was 0.050, that little funny shaped M. I'm going to cancel my M's out, and I'm going to be left with degrees Celsius because that's what we were looking for. So 3 times 1.86 times 0.050 gives us our final answer of 0.279 degrees Celsius. And that is our answer for this first problem, for number 1. So I'm going to pause for a moment. And as I like to say, I'm going to let that breathe. Okay? We're going to let that breathe so that you all can make sure that you got the right answer. Now, I want you guys to be mindful of the fact that here, there's one thing that we need to be aware of, and that is the significant digits and the final answer in terms of being negative. Here's what I'm saying right here. You remember how up here they gave us the freezing point right here of negative 2.48? Guess what? We cannot forget that negative in terms of our number, okay? Because we have to use that as a part of our final answer, okay? So here's what I'm going to show you here, all right? You see where it says 0.279? And by the way, we need to put that in terms of 3 significant digits because when we multiplied it, we have 2 significant digits here, all right? And 3 significant digits there. We don't include the Van Hoff factor as part as saying 1 significant digit. You don't include that for your final answer, but you do look at the temperature and the molality. So our answer here will be 0.28 degrees Celsius, okay? Now, what I want you all to do is when you look at your answer here, okay, our freezing point that we got is equal to 0, basically the same thing, okay? So when we look at the numbers here and we establish what we have, they do check off to being equal, all right? They do check off to being equal. And what we know, we could actually, if we go back to our previous formula, okay, let me show you all the previous formula so you all will know what I'm talking about over here, okay? You remember here where it says you can take the pure solvent, okay? The T solution is equal to the temperature of the pure solvent minus the delta T of F, okay? And if it's water, then the pure water will be 0. So in this case right here, if we go back to our problem that we were doing, okay, right here, it was dissolved in water. So guess what we're going to end up with here? If we take our temperature of our pure solvent, okay, I'm putting P of S just because of space, minus our delta T of F, and this case was water, 0 minus 0.28 degrees Celsius will give us negative 0.28 degrees Celsius. And guess what? That checks out to what was given in our problem right here. Okay? That negative 2.48 degrees Celsius. Hold on, scratch that part of what I just said. Hold on, scratch that part of what I just said. Our final answer, excuse me, becomes negative 0.28. Okay, so we in essence know that the two numbers are different. Okay, in essence, the two numbers are different. And that's because this was the freezing point of the solution itself. But what we were doing was calculating the freezing point of our barium chloride, okay, in water. All right, let's look at the second problem right here, okay? The second problem. Problem number 2. Again, I got to make this a little bit larger because, it's too small for some of you all to see. So let me go ahead and make that a little bit larger, okay? And let's scoot everything else down here. Okay. Nurse's IV solution. All right, here we go. It says a nurse mixes 0.25 moles of sodium chloride. Excuse me, let's start that over again. Excuse me. A nurse mixes 0.25 moles of sodium chloride in 500 grams of water to prepare an isotonic IV. If K of F, and let me go ahead and put that on the same line, if K of F equals 1.86, what is the freezing point of this IV solution? Assume sodium chloride's Van't Hoff factor is equal to 2. Now, by the way, what we left off here was the degrees Celsius per molality, okay? So we do need to keep that in mind, that is part of our problem here, all right? So what we're trying to calculate is the freezing point of this solution. So your delta T of F is equal to the I times the K of F times your molality. Now, in this particular problem, though, what they have given you here are the moles and the grams. So they gave you the moles of the solute, but they gave you the grams of the solvent. And remember, we have to convert that to a kilogram by moving our decimal place 3 places over to the left. So let me go ahead and do that now. Or you can divide by 1,000, but moving it over 1, 2, 3 places over is simple enough. Now, in order to do this problem, we have to calculate the molality, okay? The molality. And they already told us what the Van't Hoff factor was, which was 2. So that's a no-brainer right there. So let's go ahead and calculate our M, okay? So that we don't have to, because we could technically plug the I here and the K of F and then put the molality here in the problem. But I think it's simpler to just go ahead and plug in and solve for the molality first. So remember, it's the moles, which in this case is 0.25 moles, divided by your kilograms, which is 0.500 of your solvent, okay? So we're going to plug those numbers in right there. We've got 0.25 divided by 0.500, and we end up with 0.50, that little funny shaped M, okay? All right, now what are we going to do? We are going to now use our formula. So our delta T of F is equal to 2, because they told us the Van Hoff factor was 2, times 1.86 degrees Celsius per molality times 0.50 molality. So you already know that your M's are going to cancel out. And let's just plug these into our calculator. 2 times 1.86 times 0.50 gives us 1.86. So our delta T of F, okay, which is our freezing point, is equal to 1.86 degrees Celsius. That is our final answer for this particular problem. All right. So again, if we go back to what we were talking about, okay, we were trying to figure out what the freezing point was equal to using our formula I times K of F times molality. In this problem, they gave us the solute, they gave us the solvent to find molality. However, the moles was good, but the grams was not, and we had to convert that to kilograms. And now we solve for molality, which is in blue. Now we can use the I, which is a Van Hoff factor, times the K of F, times the molality, and that's how we ended up with our answer of 1.86. Okay, so now we are going to do another problem. This time we're going to solve for molality. Okay, so let me increase the size here. And okay, so this is where it comes into place where you have to solve for M. Now, again, here is the formula, and sometimes students may think this is redundant, but if you write the formula out every time, guess what? It makes life easier so that when you have to solve for it, you'll know what to do. So now in this case right here, we are solving for M, okay? Because it says, what is the molality of the solution? How do we know that? Well, let's read the problem. It says a substance causes the freezing point of water to drop by 1.86 degrees Celsius. If the solute is molecular, meaning I is equal to 1, and the K of F is equal to 1.86 degrees Celsius per molality, what is the molality of the solution? So what do you have to do in this particular case? We're going to isolate M by itself, and we are going to divide both sides by the I and the K of F so that it can cancel out on this side. And here you have it over here on the left side. So I'm going to rewrite this formula. The little molality formula is equal to the delta T of F divided by I times K of F. Now you're probably saying, wait a minute, I thought the formula for molality was equal to the moles of the solute divided by the kilograms of the solvent. That is correct. But if they give you other variables in your problem, then you can rearrange the original formula to solve for molality in that regard. Here's the case in point. They told you that the delta T of F was 1.86, the freezing point. So we're going to put 1.86 degrees Celsius right there on the very top. On the bottom, our I is equal to 1 right here in this part of the problem. And then they also told us the K of F was 1.86 degrees Celsius per molality. So you already know what you're going to do, right? You're going to cancel out those degrees Celsius and you're left with your molality of that little symbol M. Well, 1.86 divided by 1.86 is equal to 1 molality. So that is your answer right there for number 3. See how simple these problems can be? I know it doesn't always appear to look simple until you dig into it and start the process. Okay? You got to dig into it and start the process. All right. So let's do another example where we're looking for another part of the unknown. Okay? So let's move to, let's look at number 6. Number 6. Number 6. All right. So, of course, we got to read the problem. So we'll know exactly what we're doing. So I'm going to, y'all know the deal, make it a little bit larger. Okay. And here we are right here. Okay. Nursing lab prep. Yep. Nurses have to prep their labs to do these things. Yes, yes, yes. You prepare a solution by dissolving a drug that produces two ions in water. The freezing point drops by 3.72 degrees Celsius, and the molality is 1.00 m. What is the freezing point constant, K of F, for the solvent? Okay, so let's identify what we know in this part of our problem, okay? Let's identify what we know. It says that this drug produces two ions. So you know that's going to be your I, okay? Your I is going to be equal to two ions. The freezing point drops. So your delta T of F equals 3.72 degrees Celsius. Your M is equal to 1.00. What is the freezing point constant, meaning your K of F? That's what we're looking for. So if we go back to our formula again, which was delta T of F is equal to I times K of F times M. Okay, you can write this, several different ways. I may have put the M first the last time. Doesn't matter. It's still the same formula. Okay, just could be rearranged a different way. Because we're looking for K of F, we're going to divide both sides by the I and the M. Divide both sides by the I and the M so that they can cancel out, okay? And you're left with solving for K of F. So I'm going to rewrite that formula. And let me tell you, I tell students all the time, if you look at the main formula, what you should do is rewrite the formulas that you could solve for the other unknowns on index cards. That way, you're able to establish what the formulas are going to be for every case scenario. So if you're given the main formula, rearrange it to solve for the other ones so that you can know what the other formulas are going to be for molality, for instance, the Van Hoff factor, the freezing point constant, or the freezing point in general. Okay. So again, this is just be mindful of that. You want to write those formulas down. So all you have to do is use the one that you need. Okay. Plug and chug. So in this example here, let's go ahead and write in the numbers that we are working with. So our delta T of F is on the top. That's 3.72 degrees Celsius. Your I, they told you had two ions, and your molality was 1.00. So what you're going to do here, again, 3.72 degrees Celsius divided by 2 times 1.00 is 2 molality. Let's just plug those into our calculator. And you will end up with the K of F equaling 1.86 degrees Celsius per molality. And that is your answer for that one. So we were able to find the freezing point constant for this particular problem. Okay. All right. We're going to do one more so that you all can see how this whole process works again. Sometimes you've got to do multiple examples to get the idea of what you are doing. Okay. So let's pick one more to do. Let's see here. Let's do hmm. Oh, let's do number 9. We might do two more. Let's do number 9. Number 9. Matter of fact, and I'm going to tell you why I'm choosing number 9. Okay. So right here in number 9, it says a sample freezes at negative 1.50 degrees Celsius. It contains a non-electrolyte drug dissolved in water. If the K of F is equal to 1.86, and y'all, I keep leaving off the other parts, degrees Celsius per molality, what is the molality of the solution? Okay, let's identify what we know. First off, they told you that it freezes at negative, so let's write that in, negative 1.50 degrees Celsius. It says it contains a non-electrolyte drug. Remember, non-electrolytes, the the Van Hoff factor, is automatically equal to 1. And I wanted to do this problem because they did not tell you what the non-electrolyte drug was, but because we know it's equal to 1 because it's a non-electrolyte, that means it's not going to break apart. It goes back to that cookie example that I gave you. If I take a cookie and dunk it in water and it doesn't break apart, then that I is equal to 1. But if I dunk it and then it breaks up into 2 pieces, then that I, or that Van Hoff factor, will be 2. If it breaks apart into 3, then the Van Hoff factor would be 3. So the higher the number, the higher the boiling point. Okay, that's another little side note. Now, in this problem, we're solving for our M, for molality. Oh, and guess what else they gave us? They gave us a K of F, which was 1.86 degrees Celsius per molality. Now, you can automatically tell that when you have two units that are the same in terms of part of it, like these degrees Celsius, they're going to cancel out. Okay? They're going to cancel out. So our formula, again, is equal to delta T of F divided by your I times your K of F. So we're going to say negative 1.5 degrees Celsius on the very top, divided by the 1 times 1.86 degrees Celsius per molality. So you're basically saying negative 1.5 degrees Celsius divided by 1.86 degrees Celsius per molality. Because, 1 times anything is the number itself, okay? So our degrees Celsius is going to get canceled out. So let's plug this into our calculator, okay? You've got 1.50 divided by 1.86, and we end up with 0.806 molality. Now, I know that there is a negative number there, but you cannot have a negative molality. So our final answer is just going to be 0.806, okay? That's what our final answer is going to be. All right. Now, make sure that those of you guys that are in the live, make sure you just give this live a thumbs up because that's just going to let the analytics know, hey, this was a good video. We had some students watching. They enjoyed it. So don't forget to subscribe to us also. If you're not already subscribed to us, make sure that you do that. And make sure that you guys, thumbs us up and subscribe to our channel if you aren't already subscribed. Okay. We will do one more example. Number 10. Number 10. And again, this one should be pretty straightforward. Let's see. It says, and see, you have to understand the verbiage of these problems to know what they're telling you to do. All right. So it says a 1.50 mole solution of potassium chloride is made. What is the freezing point of the solution? Hint, potassium chloride's Van Hoff factor is 2. And the freezing point constant is 1.8 degrees Celsius per molality. Now, when you see the word molal solution, that just simply means M, okay? That's what that means. And since you are looking for the freezing point of the solution, we have to establish what formula we're going to use. It's the one that we talked about at the very beginning of this lesson. Okay, so what are we going to do right here? We're just going to plug those numbers in. The I, they already told you, was 2. The K of F, 1.86 degrees Celsius per molality. And the molality or molal is 1.50. So when they say molal solution, that's what they're talking about. We're going to cancel out those M's because we don't need those M's anymore. And we're looking for the freezing point. So our delta T of F is equal to 2 times 1.86 times 1.50, and we get 5.58 degrees Celsius. That is our final answer. All right. So I hope that these problems have been very helpful for you guys. And one other thing too, because this was talking about the freezing point, okay? The freezing point right here. They said, hey, the freezing point. What is the freezing point? You would have to know that you would place a negative sign there, okay, because it dropped. And so in this case right here, we're going to put negative 5.58 degrees Celsius. Okay, that is our freezing point of the solution. All right. So if there aren't any questions, you can always drop a comment in the comment box, okay? In order to know what, what your answer is. And make sure, guys, that you all don't forget that we will be going live Monday through Thursday here on this platform of YouTube. And let me also say this too. If there are other things that you want to see or that you need help with, don't forget to let us know, all right? So thank you guys so much for joining us. Don't forget to comment, share, and subscribe to our channel, and we will see you again on the other side. Take care.